Uh, right. So I'm Kimon, I'm postdoc with Michael Mahoney. So we are working on local graph clustering, and we'll try to do an optimization perspective of it. And that's really our initial steps in this direction. So this is a joint work with a few people from UCB and David Gleick from Purdue University. So what is local graph clustering? I will start with this, and what's the motivation? Why do we need local graph clustering? So here's an example. So the graph here, every node of this graph is an author of some paper that was published in an archive on the topic of general relativity and quantum cosmology. So every edge between two authors essentially shows that if two authors collaborated for the same project. And if some paper has many authors, then we just represent this as a click. So what do you see here? You see a graph that has lots of small-scale structure and nearly no large-scale structure, which means that it has lots of small graphs and no large-scale graphs. Clusters. And actually, even the ones that you cannot see, that might be there. Small-scale clusters. It's difficult to visualize them with the current visualization software. So what do we need from this graph? We need to find these small-scale clusters. And the first step will be to try some global graph clustering algorithm, which is normalized cuts, and that will give you the red and the yellow cluster, right? But you might, there are other small-scale clusters in there, so you might want to recover those as well. So one way to do this, which we work with, is local graph clustering. So what this does here is given a seed set in the cluster, just a single node, then we can run some diffusion or some spectral algorithm, we'll discuss it later, and then we can recover this cluster. So this cluster, it's all different than the ones that you get from global clustering. Now this is a toy example, really. What happens when you have a difficult, a messy graph from some social network? So this is a Johns Hopkins Facebook network from 2005. So graphs like this are messy. They are messy in the sense that they are not clear clusters. There are some clusters there, but they are well connected with other clusters, so it's difficult really to define what the algorithm will recover in this case. So what you see here is every node is a student. The color means class year of the student, and I did my best actually to visualize it such that some of the clusters at least are clearly visible. Usually you will get a hairball if you try to run a standard visualization software. But anyway, that's not the topic here. So there's a large cluster of students from 2009 and some other cluster next to it. So this is the purple cluster, and there's some other cluster which is close to it, which is probably some student belonging, which they stay in some dorm. So again, what we want to find here is we want to find some of these clusters. If we run a global procedure normalized cuts, what we will get back is we'll get a cut, which is noted here by the yellow nodes. And this is about 20% of the graph. But I might want to recover, as I said, we might want to recover small-scale structure in this graph. And for example, I might want to recover this cluster, which is just 3% of the whole graph, right? 3% of the nodes. So of the volume, sorry, of the whole graph. And again, you can do this by doing local graph clustering. But this is a relatively difficult cluster to get because you can see there are many edges coming out of it. So it's a nice thing, that this local graph clustering seems to work. And even more difficult cases where you have, this larger cluster that's even more well connected internally, which is a bad thing for the notion of a cluster, and you can still recover stuff like this. There are some nodes that we miss actually, outside the cluster, but it still works fine. So this, how do we find these clusters? This is mainly motivated, algorithms that exist are mainly motivated from the theoretical computer science perspective. And what these people wanted to answer is essentially, I have a small scale structure and from a huge graph, probably up to billions of nodes, and I want to recover the small scale structure in running time that depends only on the size of the output cluster. And so it's mainly a running time argument, from the theoretical computer science perspective. And so there are many algorithms that have been developed over the years. This is just a few of them that, in my opinion, they're sort of the most well-known. There are many good people working on this. There's Satish Rao from UCB, there's Spielman, Anderson, Chan, and Leng, who did nice work on spectral methods. So we'll briefly discuss some of them today, just because I'm going to use them to demonstrate some experiments. Yeah, not in great detail because there's so many details in this paper that it's difficult to go over them in the talk. So briefly, all these algorithms, they are separated in three parts. Well, they are the global, the weakly, and the strongly local algorithms. Now, what does it mean? Global algorithms, what will do is they will try to capture the large-scale structure of the graph, and the running time depends there on the size of the whole graph, right? So we touch the whole graph there. And there are weakly local algorithms, which is given a seed set, then I'm trying to recover a solution that is locally biased, but the running time again depends on the volume of the whole graph. And then finally, there are strongly local algorithms that what they do is, given a seed set again, I'm trying to find fine structure in my graph, and I want to find this in running time that depends only on the volume of the output cluster. So I pay running time which depends only on the output solution. Okay, so here's an example that demonstrates this difference. So we have what is the graph here? The graph, every node is a senator. An edge between two senators essentially shows that if the senators, they voted the same bills within a 2-year Congress period. So we have Congresses here from 1789 up to 2008. So what happens here is when we run the global algorithm. Well, this graph is essentially separated in two parts. One part is before 1910, and the other one is after 1910. Essentially, is before and after the American Civil War. So global graph clustering algorithm will find exactly this. This separation of before and after the Civil War period of the new era of American politics. So, but we might not want to find this large-scale structure. We might want to find some finer structure, which means that I can just plant some seed set just out after the Civil War period, and I want to explore the voting patterns for some congresses, locally. So what I do is I plant the seed set, which is denoted here by the yellow nodes with the blue halo around them. And what happens here is the weakly local algorithm will touch the whole graph. That's why you see here every node has a color, which means every node has a weight. But the colors around the seed set are brighter, and essentially that means that the solution is locally biased. And you can find a similar solution using a strongly local algorithm without even touching the whole graph. So briefly what the strongly local algorithm does, it starts diffusing information from the seed set, and at some point we terminate early based on some criterion, and then we recover a cluster. So now this shows that that means weakly local algorithm scales up to thousands of nodes, strongly local algorithm probably scales up to billions of nodes, but really it's not that strongly local is better than weakly local. There are experiments actually that you can come up with that weakly local gives a totally different solution. So it really depends on you, the application, if you want to find some particular cluster or if you just want to find a cluster fast. So in the last case, you probably use a strongly local algorithm, for example. Okay, what are these 4 of these algorithms? What are they doing? So they are mainly spectral, which are algorithms which are shown on the left, and they are flow algorithms which are shown on the right. So on the left, first is MOV. MOV is weakly local. What it does, it looks for the second eigenvector from the normalized Laplacian matrix. And it does this subject to some constraint that represents locality with respect to the seed set. And there is ACL. ACL is a simple random walk. Essentially what it does, it solves approximately the personalized page rank linear system, and you terminate early. And there are the improved algorithms, which what they do is they take as input the solution of some spectral algorithm, or some actually any seed set that satisfies particular criteria, and then it tries to improve it by doing a sequence of max flow min-cut computations. And there's a local flow version, which is let's say, a clever way of doing the max flow commutation such that we don't touch the whole graph. Okay, that comes with a cost as well, as we'll see later. Okay, I haven't defined the notion of a cluster yet. What cluster means, at least from the computer science perspective, and what we can gain by having this optimization perspective. So if you ask a computer scientist, probably they will, what is a cluster, or maybe everyone here, probably they will tell you a cluster is something that is poorly connected externally and nicely connected internally. So this is captured by conductance, okay? Conductance, like Michael would say, the big elephant in the room in these applications. So theoretical computer scientists would say, this is my notion of cluster, I want to minimize this. But this is an NP-hard problem, so theoretical computer science people are clever mathematicians. What they did, they came up with some approximation algorithms, and here's how the local graph algorithms, spectral and flow, they come into this game. So the problem is the following. When, as a practitioner, when I try to solve, actually use these algorithms, is that it's good that I know that they capture some notion of clustering. The problem is that each one will give me a different solution. And here's an example that demonstrates this. So on the left, you can see the seed set that I gave here is Minneapolis plus suburban areas. So this is denoted by yellow plus orange. And I run a flow algorithm. The flow algorithm will give me the orange part, which is essentially Minneapolis plus a little bit of suburban areas. Then I have a spectral algorithm, and that will give me Minneapolis exactly. Now, in terms of conductance, they are very similar. So what is best? I don't know, maybe if you ask the computer science, they will tell you the one that gives you the best conductance is the best cluster. If you ask the practitioner, maybe they will tell you that Minneapolis, the right algorithm is the best. So that really depends on you, but it just shows that the relaxation that happens there from the NP-hard problem to the relaxed problem is actually imposes some properties in the solution, and this is what we are trying to figure out by the optimization perspective. So yeah, this talk is about So this talk is about an optimization perspective, which what we'll try to do is try to find a unified framework of all these theoretical computer science algorithms. And we hope that this will show some regularization properties about the solutions. And so there are three common factors, actually, that characterize this unified framework. The first one is how do we incorporate localizing bias? How do we incorporate information from the seed set in the solution? The third one is how do we measure distances among the nodes, L1 or L2 metric? And then how do we impose strong or weakly local running time for the algorithm? Now, having this optimization perspective, we can leverage state-of-the-art optimization algorithms which have similar or better running time in theory and in practice. And then we can also parallelize them and have distributed versions of this. So I'll mainly focus on the optimization perspective today, but I'll also briefly mention the optimization algorithms part as well. So first factor in this optimization framework is localizing bias. Where what we need here is we need this notion of augmented graph. What's an augmented graph? On the left, you can see here some given graph, simple unweighted graph. And then what the augmented graph is, we need to introduce a source and a sink. And we also given a set R, which is denoted here by the red circle. So what we do is we connect the source to the set R, and the rest of the nodes, we connect them to the sink. Okay, now and then we also have to add some weights and some parameters alpha and beta. But how really this shows that why this augmented graph promotes locality. An example that you can think of is, let's say we want to send some flow from the source to the sink. Now, the flow will have to necessarily pass from the set R. So if there's a bottleneck there, the solution is going to be locally biased. So very briefly, an example that this is an example that why this structure here promotes locality. So metrics, how do we measure distances among the nodes is really important. It will really make a difference in the solutions. And here I'm just demonstrate some examples and some maybe conclusions that, if I'm allowed to say, some generalized conclusions that we can extract here. So this is US roads again. So we have E is a set of nodes, a set of edges from the augmented graph that I showed before. And we have two matrices, B and C. B is the incidence matrix, or otherwise the graph derivative. And then we have the C matrix, which is a diagonal matrix that captures the weights of the edges of the augmented graph. So why was, in the example that I showed before, why was the solution different? Well, the difference is because we measure distances of the nodes in different way. So the flow example actually measures distances with respect to the L1 norm. Okay, the spectral embedding measures distances with respect to the L2 norm. And actually there's theory that backs this up and says that spectral or otherwise the L2 metric, essentially, it finds clusters that are well connected internally. Now, this is a simple case, really. I just I chose this example because I want to have a clear demonstration of what's going on. But let's see what happens in difficult graphs. Now this is a Berkeley Facebook graph from 2005, I think, I guess. So this graph is messy. Again, I tried to visualize it nicely. So I will mainly work with a cluster on the top of the black nodes, which are students from 2008. So let's see what happens when on this L1 versus L2 thing for this graph. Now, what do the colors mean here? Yellow plus orange on the left is the seed set. And what the solution, when we run a flow algorithm, what happens is that it finds the red plus orange. So it actually leaves, so what I did here, I gave say, difficult seed set, which means I gave some nodes within the cluster of the students of 2008, and I also gave some irrelevant students, but which were connected with this cluster. So what the flow did is here is it tried to find nice boundaries, so it left outside the nodes that are sort of not in this cluster. So it gave us, a relatively decent, cluster for those students. On the other hand, what the spectral algorithm will do, it will do exactly the opposite. It will try to diffuse information from everywhere. So that's the reason you see here that it sort of finds the cluster, but also there's these little red nodes that means that there was lots of information that was diffused that is not useful. And actually, this is after rounding. So I actually try to round the solution based on some, again, theoretical computer science rounding algorithm, which has some particular guarantees. But this is what you get. So as a rule of thumb, I would say that spectral leaks mass outside the boundaries. Flow just tries to find better boundaries, better, poorly connected clusters. Same thing for the John Hopkins graph. Again, I gave a similar seed set, which is, partially inside the cluster, and some of the nodes are outside the cluster. Again, flow tries to find nice boundaries. Spectral leaks information a lot. Another example, the Sennett graph. Exactly the same scenario. Flow finds good boundaries. Spectral seems to miss that, doesn't have this property. And here's an example where the cluster that we try to recover is actually so simple that essentially the L1 versus L2 thing didn't make a difference. Both algorithms recovered the same thing. Okay, now third factor is weak and strong locality. Now I said before that strongly local algorithms will have strongly local running time. They are not necessarily better. And here's an example that demonstrates this. So this is the Sennett graph again. So on the left, you can see a weakly local flow algorithm. On the right, you can see a strongly local flow algorithm. Now, what happens when we allow the algorithm to explore the whole graph? Well, it finds a cluster which is red plus orange here. Because spectral actually what we'll do is we'd like to find a cluster which has large volume, right? And it's also poorly connected externally. And this is exactly what happens here. The problem is that this scales up to thousands of nodes because the running time depends on the volume of the whole graph. On the other hand, the strongly local algorithm will try to have a strong overlap with the input seed set, and that's what actually gives the strongly local running time, which means that the running time, we can run algorithms like this up to billions of nodes, essentially. Okay, spectral, the same conclusion with respect to the running time. It happens in this case that the two examples give similar clusters, so maybe that means that running a strongly local running time is better in this case. So let's put everything together, all these three properties. Now, the first one is localizing bias. Now, this is captured by the matrix B. Everything is, the bias of the solution towards the seed set is captured in the matrix B. Now, if it's a flow, we just measure distances with respect to the L1 norm. If it's a spectral, we measure distances with respect to the L2 norm. And what happens if we want to have a sparse solution? Then we simply impose some L1 regularization. So L1 regularization sort of gives us a sparse solution, and this is exactly the same scenario for flow and spectral. We can have L1 regularized flow and L1 regularized spectral. The problem here is that, yes, the solution is sparse, but the intermediate steps of the algorithm might not be sparse. So are there algorithms that guarantee that the intermediate solutions are sparse as well? So the running time depends only on the sparsity of the output solution? Well, as I said before, yes, there are a few. So for example, flow improve is weakly local, and local flow improve is strongly local. So local flow improve essentially solves this L1 regularized L1, and strongly local spectral, which is the diffusion process, solves this L1, L2 problem. Okay, so algorithms. So what can we know, as I said before, ACL is a diffusion process, and I said that it solves this optimization problem. But why is this true? Well, ACL tries to solve the PageRank linear system approximately. This means that it has a particular termination criteria, and what we observed here, and also actually that was first observed by David Gleit, is that the termination criteria of ACL essentially are implied by the optimality conditions of this L1 regularized problem. So that's how we know what ACL solves essentially. And now having this optimization problem, then we can ask the question, you know, people from the optimization community have been working for years on proximal gradient descent algorithms and accelerated versions of those, so let's try one of these. So we tried it, and although we tried a full proximal gradient descent method, that means that in general you touch every node, actually the running time of the algorithm was strongly local. And we proved this, that, you know, the running time of the proximal gradient descent algorithm for this problem depends only on the volume of the nodes that are non-zero at optimality instead of the volume of the whole graph, all right? And this opens the door to accelerated version of proximal gradient descent, which actually will mean that we can have algorithms, strongly local algorithms, which have very nice dependence on the condition number of the problem as well. Now, Julian came in and he said, you know, I can parallelize this stuff. So he made an extremely nice state-of-the-art implementation of parallel gradient descent. And then we tried this on problems of millions and billions of nodes, which are shown on the table on the left. And we saw that essentially the algorithm can be 10 to 20 times faster on a 40-core machine. What you see here on the right is the self-relative speedup for each of the problems on the left as the number of cores increase. So it's pretty nice scale with respect to the number of cores. And actually this, as he said yesterday, this is the reason that we're able to ask statistics, you know, on various graphs that are, you know, of billions of nodes. So then many of these spectral algorithms, again, they actually reduce to solving a linear system, as I said many times already. So Adi, who works on parallel distributed algorithms, then asked the question, you know, we can have, you know, data on distributed on various machines. Then how can we solve this problem efficiently without communicating much? And why? And then we chose coordinate descent. Why do we choose coordinate descent? Because we don't have to run the diffusion process forever. We just need to run it for few iterations and then stop. So we don't need highly accurate solutions. So what we can show is that we decrease the number of messages and words that are moved by a factor of S. And actually, this is the first time that, you know, at least to my knowledge, the best of my knowledge, that we can prove that in absolute sense we decrease the number of, the amount of communication that happens in this coordinate descent algorithm. So what we did is we took the algorithm, we unrolled the iterations, we unrolled the loop, and we reorganized the computations of the algorithm in a different way such that we communicate less. So we increase the number of flops compared to coordinate descent versus communication avoiding coordinate descent, which is shown in the second column in this table. But on the other hand, we decrease by a factor of S the latency, which is the dominant communication, the dominant term in the running time of the algorithm. And we also can find a better trade-off for the bandwidth, the amount of data that are moved for the coordinate descent algorithm. So large-scale experiments for this are coming soon. Yeah, so summary future work. We find a general framework for these algorithms. Hopefully we can use it to, you know, answer questions like what are the regularization properties of the solutions, new optimization algorithms which are parallel distributed. Short-term objective is, you know, how can we get both of those two worlds, you know, good boundaries and well-connectedness. So this, how can we combine L1 and N2 objectives in a single objective? And there are a bunch of directions, actually, we just barely scratched the surface here that one can follow to extend this work. So that's it. Thanks a lot.